Hi there, and welcome to Chapter 9. We're going to spend these first three sections here in Chapter 9 talking about sequences and summation notation and some different types of sequences. Now, first of all, a sequence is just a series of terms. It says we may regard an infinite sequence as a collection of real numbers that is in one-to-one correspondence with the positive integers. Each number, a sub k, is a term of the sequence. The sequence is ordered in the sense that the first term, a sub 1, there's a second term, a 45th term, a 46th term, and an nth term somewhere along the line. Sequences do not necessarily have to have any pattern to them. They can just be a set of numbers, but sometimes there will be a defining pattern and characteristic, and we're going to look at some of those as we go along here in this section. The first definition here, an infinite sequence is a function whose domain is the set of positive integers. And you say, well, let's see, what's up with that? Now, see, we've got a sequence here that's defined as -1 to the n times 6 minus 2n over the square root of n plus 1. So here's the way this works. The first term of this sequence is defined by -1 to the, now you see n here is 1. Alright, -1 to the 1. And then we're going to multiply by 6 minus 2 times 1 over the square root of 1 plus 1. Alright, so this gives me -1 times 6 minus 2 is 4 over the square root of 2. And so this gives us -4 over the square root of 2. And of course we could rationalize this here. -4 root 2 over root 2 times root 2, which gives me -4 root 2 over 2, which gives me -2 root 2. The second term, a sub 2, well, we're going to put now a 2 in where the n was at, -1 to the second times 6 minus 2 times 2 divided by the square root of 2 plus 1. This gives me 1 times, this is 6 minus 4, which is 2 over the square root of 3. If we want to, we can rationalize this, 2 root 3 over 3. The third term, a sub 3, -1 to the third, times 6 minus 2 to the 3, divided by the square root of 3 plus 1. So we've got -1. Here's 6 minus 6, which is 0 over the square root of 4. So we have 0 for the third term. The fourth term, a sub 4, -1 to the fourth, times 6 minus 2 times 4 over the square root of 4 plus 1. So we get 1 times 6 minus 8 is -2 over the square root of 5. And so we get -2 square roots of 5. And then the eighth term, a sub a, equals -1 to the eighth times 6 minus 2 times 8 over the square root of 8 plus 1. So we've got 1 times the square root of 6 minus 16 is -10 over the square root of 9. This gives me -10 over 3, and so that's the eighth term. And that's how we go about finding the terms in a sequence. Now, you say, well, it can't all be quite that easy, can it? Well, maybe not, but when we step it up a notch, it's not too bad. For some sequences, we state the first term together with a rule for obtaining any following terms. We call this a statement, a recursive definition, and the sequence is said to be defined recursively. Let's see what we mean here. We want the first 5 terms of this. Well, a sub 1, we're told, is 5. Now, a sub 2, guys, is 7 minus a sub 1. Notice over here that a sub k, the subscript here, is 1 less than this subscript. So a sub 2, this subscript here is 1 more than what this one is. And this should be here just an a sub 1. Alright, so 7 minus a sub 1, well, a sub 1 is 5, so a sub 2 is 2. A sub 3 is 7 minus, oh, and pardon me, that's supposed to be 7 minus 2 times a sub 1, so 7 minus 10. 7 minus 10 is going to be negative 3. 7 minus 2 times negative 3. Well, this is 7 plus 6. 7 plus 6 is 13. A sub 4, this is 7 minus 2 times a sub 3. Well, this is 7 minus 2 times, what's a sub 3? A sub 3 is 13, so 7 minus 26 gives me negative 19. And then a sub 5. 7 minus 2 times a sub 4. And we know what a sub 4 is. 7 minus 2 times what's a sub 4? It's 19. 7 minus 38 gives me, actually that's a negative 19. 7 plus 38 gives us 45. Alright, so there's our first 5 terms of this recursively defined infinite sequence. This goes on forever, and it keeps going back to the recursive definition. Let's take a look at another example here of a recursively defined sequence. We've got the first term. Now the second term here, a sub 2 is equal to 1 over a sub 1. Well, a sub 1 is 3, so a sub 2 is 1/3. Now a sub 3, what do we have here? Well, this is 1 over a sub 2. Alright, well, a sub 2, remember, is 1/3. Well, 1 divided by 1/3 is 3. So my third term here is 3. A sub 4 is 1 over a sub 3. A sub 3 is 3, so a sub 4 is 1 over a sub 3. A sub 4 is 1/3. And then a sub 5, are you dizzy yet? A sub 5 is 1 over a sub 4. A sub 4 is 1/3. 1 divided by 1/3 is 3. So here are our first 5 terms of this recursively defined sequence. Now, we have some theorems here that help us out with some results. First of all, let's introduce some new notation for you. This guy right here is the Greek letter sigma, and this indicates a sum, and a sub k represents the kth term. K is what we call the index of summation, or the summation variable, and the numbers 1 and m indicate the smallest and largest values that k will take on. You see here we add a sub 1 plus a sub 2 plus a sub 3 plus a sub 4 all the way up to a sub m. We have some theorems here that say if you are summing a constant n times, so if I have the sum from k equal 1 to 3 of 7, a sub 1 plus a sub 2 plus a sub 3, this is 7, plus 7 plus 7, which is 21. Okay, and that's probably the easiest way. Now, if we're going from k equal m to n, in other words, we don't get to start at the beginning, then we're going to subtract the number between n and m, add 1, and then multiply by c. Alright, and we've got some other results here. The sum of two terms is the sum of each of the individual terms. Alright, right now we are keeping our sums very basic, and let's take a look at what we have here. If k equals 1, we have 10 minus 3 times 1. Plus, when k equals 2, we have 10 minus 3 times 2. When k equals 3, we have 10 minus 3 times 3. When k equals 4, we have 10 minus 3 times 4. When k equals 5, we have 10 minus 3 times 5. And when k equals 6, we have 10 minus 3 times 6. So 10 minus 3 is 7, 10 minus 6 is 4, 10 minus 9 is 1, 10 minus 12 is negative 2, 10 minus 15 is negative 5, and 10 minus 18 is negative 8. We add these up to get a grand total of negative 3, and the value of this sum is negative 3. The value of this sum is negative 3. I'm going to make a change here from what we see. I know this says the sum from k equals 0 to 5 of 3j plus 2. We're going to call that, this is not going to be 52 that we're going to do here. We're going to make a change. This is going to be the sum from k equals 0 to 5 of 3k plus 2. And so k equals 0 is going to look like 3 times 0 plus 2. K equal 1 going to look like 3 times 1 plus 2. K equal 2 is going to look like 3 times 2 plus 2. K equal 3 is going to look like 3 times 3 plus 2. K equal 4 is going to look like 3 times 4 plus 2. And k equal 5 is going to look like 3 times 5 plus 2. Alright, so we've got 0 plus 2, which is 2, plus 5, plus 8, plus 11, plus 14, plus 17, and so let's see, 7 plus 8 is 15, 26, 26 and 14 is 40, 57. So our sum here is 57. And guys, a nice short lesson for section 9.1. So you've got some discussion questions, got some problems to work. You have any questions, let me know.